Hello students, welcome to SuperProfs. The course which we are studying is Digital Electronics and this is lecture 10 on sequential circuits. So up till now I want to give you the recap of the subject what we have studied till now. With the starting we have started with the number systems, and in number systems we have seen different kinds of number systems and what are the input combinations for logic 1 and logic in the form of logic 1 and logic 0 for 2 input, for 3 input, for 4 input systems. Next we have studied about the logic gates and how different gates and the combination of different gates results in a truth table depending on the input combinations. Then after we have studied Boolean algebra, in which we have studied how to minimize a logical expression either by using the Boolean laws or by using the K-map. So with the help of the K-map we are able to reduce our Boolean expression into much simpler form so that it can be easily understandable. Okay, so from then we have studied combination circuits. In combination circuits we have seen different kind of things like arithmetic circuits, that is half adder, full adder, half subtractor, full subtractor, different code converters like binary to gray code converters, 2's complement adder, BCD adder. And next we have also studied multiplexers, demultiplexers, decoders, encoders, and parity checkers and generators. And we have also solved previous year questions on all the topics that we have covered till now. Now we are going to start sequential circuits. So students, it's very important to understand this concept of sequential circuits because you can expect at least 1 to 2 questions in your GATE exam based on sequential circuits. Because if we are expecting from digital electronics about 2 to 3 questions in an exam, then at least 1 question would be always of sequential circuits. So either it can be the normal concepts of flip-flops, or it can be either on registers, or it can be of counters. So it is very important to first know the basic of sequential circuits and how we are able to construct various flip-flops using the logic gates and what we are doing in that logic gates, what is the working and of latches and flip-flops. Then we will read registers, how the manipulation or how the logic 1 or 1 bit or 2 bits can be stored in our flip-flops. Then we are going to see counters, in which we are able to count the digits or we are able to count the number of clock pulses using these sequential circuits, and then we are going to see its problems related to the previous year GATE. So let us first start with the introduction of sequential circuits. So first, to understand what is a sequential circuit, we are first making the comparison between the combinational circuit and sequential circuit. So it is no need to write these points, but it is important to understand just the difference between the sequential and the combination circuit. So in the combination circuit we have studied that the present output only depends on the present input. That means whatever input we are giving at the point of time, at a particular point of time, the output that we are getting would be totally dependent on the present input only. We have seen in the circuits also there is no feedback present, so that we can say that it is also depending on some other parameter. So in the combinational circuit, the present output only depends on the present input. But there is a contrast point in the sequential circuit, in which we see that the present output not only depends on the present input but also depends on the past output. What do you mean by the past output? Suppose you can see the definition. The present output not only depends on the present input but on past output also. So suppose we have a sequential circuit. Any circuit would be consisting different types of logic gates available with us. So if this is a sequential circuit and we are representing or we are giving this sequential circuit an input, okay, the output that we are getting would be this. And suppose this is again feedback to this circuit and depending on these two parameters, the next output would be available. It means in the circuit, if there is feedback available, then we can say that the present output not only depends on the present input but also on past output. Okay, so this is the major difference between combinational circuits and sequential circuits. One more difference that would be very important regarding these, considering these points only, that combinational circuit is a memoryless system, because we are not storing any output or input so that it can be manipulated later. But in a sequential circuit, it is a memory system. It is having a memory, because to get a next output, we are dependable on the previous output or the past output. So we have to store somewhere this past output so that it can be used in the next stage. So we can say that a sequential circuit is a with memory system. And similarly, combination circuits are faster and sequential circuits are somewhat slower in comparison with combination circuits. The reason is very obvious, that in combination circuit, the present output is totally dependent on present input, so there would be no much delay. But in the sequential circuit, the present output is depending also on the past output, which takes some time to travel and it would produce a delay. That's why we can say that the combinational circuits are quite faster or having a fast response than the sequential circuits. Okay, so these are some basic points regarding the combination circuit and the sequential circuit difference. So let's start with the introduction. First, we can see that flip-flops are the basic memory element. So when we are going to study the flip-flops, we can see that we are able to store a 1-bit memory in a flip-flop. So we can say that flip-flops are the basic memory element, and it can store a 1 bit of information. What is a 1 bit of information? Students, logic 1 or logic 0 can be regarded as a 1 bit of information. Okay, so it has two stable states, hence it is also known as bistable multivibrator. Two stable state means, student, it can store either logic 0 or logic 1. Okay, so it would having a two stable state, that's why it is known as a bistable multivibrator. And the simplest form of the flip-flop is known as latch. So the simplest form is known as latch. So to understand or to start with latches and the flip-flops, first we need to understand what is triggering. So triggering is used to initiate the operation of latches or flip-flops. So you can see the triggering is used to initiate the operation of latches and flip-flops, and the main purpose of triggering is to synchronize latches. Okay, so we can write the main purpose of triggering is to synchronize the latches. Okay, so there are two types of triggering that is available. First is level triggering and second is edge triggering. What is the difference between level triggering and edge triggering? In the level triggering, suppose if we are drawing a clock pulse like this, okay, and if we are triggering at level 1, this is logic 1. So if suppose we are triggering a flip-flop at level 1, it means that the inputs that we are giving to a system would affect the flip-flop only in this area, that is in logic 1. It means the flip-flop will be affected by the inputs given only when the triggering is at level 1 or at logic 1. Or if we are triggering a flip-flop at logic 0 or active low logic, then it would be the working of the flip-flop would be affected on logic 0. So this is known as level triggering, either at level 0 or level 1. But in edge triggering, what is the method? Suppose we are changing the inputs, or if we are affecting the working of the flip-flop or the outputs of the flip-flop during the transition from either 0 to 1 or 1 to 0. So suppose if we are either changing the or affecting the flip-flops when the clock pulse is rising from 0 to 1 either on this edge, or if we are affecting the working of flip-flops on the falling edge, that is from 1 to 0, or we can say that from the transition from 1 to 0, then we can say that it is a edge triggering type. It means that we are changing or we are affecting the flip-flop or we are manipulating the flip-flop during the falling and the rising edge of a clock pulse. So it is very important to understand what is triggering. So okay, and we have also studied what is a sequential circuit. So sequential circuit, the present output not only depends on the present input but also on past output. So you can write these points, then we are going to see how the sequential circuit is constructed and what are the basic types of latches. Okay. When you going to see what are the latches and how the construction is done, you will be able to see the presence of the feedback in the circuit, which just implies that we are depending on the past output also for our next output. Okay, so let's start with the first latch, which is NAND gate latch. So first I am drawing the circuit and simultaneously I am writing its truth table. So you can write or you should write both under this heading directly. Then we are going to see its working. So don't write or don't do the working that I am explaining on the main circuit. Keep it clean. If you want to know or if you want to write the working also, you can write or you can make a separate circuit and then you can write the zeros and ones on the basis of your understanding. So make a circuit with a NAND gate latch. We are using two NAND gates like this and one more NAND gate like this. Okay, suppose we are giving here input S and we are giving input R. So S and R doesn't stand for very any much thing. It's just representing S for set and R for reset. Okay, so now we are going to give the feedbacks from the output side. This is the presence of feedback. Okay, and the output that we are getting is Q. We are representing it with Q and Q bar. So we have marked this Q and Q bar. The NAND gate will not understand what we are taking from outside. So we also should write the truth table for this circuit. So if we want to write its truth table, the input combinations, there are two inputs, that is S and R, and we are taking output Q plus. Q plus stands for the next output. Okay, so for 0 0 0 1 1 0 and 1 1 we have to write the output. So for 0 0 it would be a don't care condition. Okay, for 0 1 it would be set or logic 1. For 1 0 it would be reset or logic 0, and for 1 1 it would give us a memory state. So you can make this circuit diagram and you can write the truth table. Then I would going to be start teaching what is the functioning and what is the working of a NAND gate latch. So to understand the working of this NAND gate latch, we have to take assumptions. Okay, so the first case is if we are taking the first input condition, suppose we are taking S equals to 1 and R equals to 1. Okay, so S is also 1 and R is also 1. So to understand what would be the output, initially we have to take a past output. So suppose we are taking Q as 1, so Q bar would be 0. Okay, now we have to know what would be our next output. Okay, so as we are taken S equals to 1, I am marking in this circuit only. If you want to understand, or you can write the working by making another circuit and marking these points. Okay, so suppose S equals to 1 and R equals to 1. We have taken Q equals to 1 and Q bar equals to 0. This Q would transfer at this point and this Q bar would be transferred at this point. Okay, so 1 and 0, what would be the output? So for 1 and 0, the output would be 1. So it is changed to 1. And for 1, 1, when inputs is given to a NAND gate, the output would be 0. So you can see that there is no change in the next output from the past output. Okay, now take second condition, that is if Q was 0 and Q bar was 1. Okay, so we are interchanging the values, so you can change here if Q was 0 and Q bar was 1. Okay, so for Q for 0 it is 0 and this would be 1. So when inputs 1 1 is given to this, it would lead to 0, and for 1 0 the output would be 1. So in this condition, or in this case also, there would be a no change in the present output from the past output. So we can say that Q plus would be in memory state, that is Q. Okay, it is in memory state, that is there is no change in the next output from the past output. So if S equals to 1 and R equals to 1, it stands for memory state. Okay, now we have to see the next condition. So first I erase these points to avoid confusion. Okay, so to avoid confusion, I have removed all the logics. Now suppose we are writing our second case, that is if S equals to 0 and R is equals to 1. So we have to consider again if Q is equals to 0 and Q bar is equals to 1. Okay, so we have taken S equals to 0 and R is equals to 1, and we have taken Q equals to 0 and Q bar equals to 1. Okay, so 0 would come here and 1 would come here. So 0 1 AND gate would give us 1 and 0 1 AND gate would give us 1. So we are getting output as Q equals to 1 and Q bar is equals to 1. But this is not the final stage. This is an intermediate stage, and again we give these outputs again to the NAND gate as a feedback. So it is 1 and it is changed to 1. Now 0 1 AND gate would lead to 1 and 1 1 AND NAND gate would lead to 0. Okay, so the final stage that we are getting, why we are saying this as final stage, because now if we give again Q as 1 and Q bar as 0, there would be no change in the output. So 0 0 would lead to 1 only and 1 1 would lead to 0 only. Okay, so the final stage for S equals to 0 and R is equals to 1 is Q is equals to 1 and Q bar is equals to 0. Okay, so this is our final stage. The same we have written here for S equals to 0 and R equals to 1. The Q plus or the next output would be in set condition, that is logic 1. Okay, from this we can see that. Similarly for the second case, that is Q equals to 1, Q bar equals to 0, we can prove the same thing, that is Q would come as 1 and Q bar would come as 0. So this was the second case, that is for S equals to 0 and R equals to 1. Okay, I hope you have understood this condition. Now we are taking our third condition, that is S equals to 1 and R equals to 0. Okay, so suppose we are writing our third condition, that is C is S equals to 1 and R is equals to 0. So taking first case, that is, let us assume Q equals to 1 and Q bar is equals to 0. Okay, so for S equals to 1 and R equals to 0, we have assumed that the past output was Q equals to 1 and Q bar is equals to 0. So this 1 would be transferred here and this 0 would be transferred here. Okay, so 1 0 NAND gate would give us 1 and 0 1 NAND gate would also give us 1. So similarly in the previous case, this is again not the final stage, because again the output would going to be changed, because this feedback will again go to these NAND gates. So if it is 1 and this is 1, now 1 1 NAND gate would result in 0 and 0 1 NAND gate would result in 1. Okay, now if we again give this 0 and 1 to this NAND gates, there would be no change in our output. It means that the final stage or the stable stage for Q is 0 and for Q bar it is equals to 1. Okay. Similarly, if we want to check for the second assumption, that is Q equals to 0, suppose if past output was 0 and Q bar is equals to 1, then again we are going to see that Q would come as 0 and Q bar would come as 1. So now the third case is also proved, that is for S equals to 1 and R equals to 0, we are getting the reset condition, that is logic 0. Okay. Now we are going to prove our fourth case, that is for S equals to 0 and R equals to 0, why we are taking a don't care or invalid state. So let us remove these logics. Okay, let us remove this logics. Now to understand how the circuit is changing or manipulating the logics, we are taking S equals to 0 and R equals to 0, and our first assumption is, suppose if the previous output was 0, Q equals to 0 and Q bar is equals to 1. So we have assumed Q equals to 0 and Q bar equals to 1. So this would come here 0 and this would come here 1. So 0 1 NAND gate would result in 1 and 0 0 NAND gate would also result in 1. Now again transfer this 1 to this point and this 1 to this point. So 0 1 NAND gate would result in 1, 0 1 NAND gate would result in 1. So we can say that this output is Q equals to 1 and Q bar is also 1. So we are taking this condition as don't care condition, because we have assumed outputs as Q in normal form and the second output that we are getting from this point is Q bar, that is its complement. But for both the conditions we are getting Q equals to 1 and Q bar also equals to 1. So this is not a proper state that we are expecting. This is complementary. This is against our assumption of that we have taken, that the outputs we are giving as Q and Q bar. So as both the outputs are coming as 1 1, we are considering as a don't care. That means we are not considering or we are not caring about this output, or we can say that it is an invalid state. So for Q equals to 0, for S equals to 0 and R equals to 0, Q is and Q bar is equals to 1, or we can say that it is an invalid state. Okay, suppose we have assumed that Q was 1 and Q bar was 0. So if we put these 2 points also, we are getting the same result, that is invalid state. Okay. So for the 4 input combinations, we have understood why we have written this kind of truth table. And what is the working of NAND gate latch? So I hope you have understood this NAND gate latch clearly, because next all the latches and flip-flops, the working would be exactly the same, just the logics would be reversed or the truth table would be reversed. The working of any latch or a flip-flop would be same as this working. Okay. So the outputs may change, but the working won't change. The working would be similar to this. And one point also, why a NAND gate latch is known as active low mode, because for a NAND gate, we know that if we give any logic as 0, the output we are getting as 1. So this NAND gate would be active when we are giving as logic 0, and the output we are getting as 1. So always for logic 0 as input, the output would be 1. That's why we are saying that it is an inactive low mode. So you can write these points. Next we are going to see our NOR gate latch. I hope students you have understood the NAND gate latch very clearly, because the next latches would be on the same principle. So let us study the NOR gate latch, or we can say active high mode. So why we are saying this as active high mode? Because on giving an input active high, we are always getting a output 0. So when we give a logic level high, the output would always be 0. So we can say that we are activating this NOR gate by giving an active high mode. So for NOR gate latch, we are drawing the circuit and writing its truth table. So just write its logic circuit and truth table. The rest of the functioning and the working would be same as the NAND gate latch. So we are taking two NOR gates. Okay, we are taking two NOR gates with us, and we are now giving it feedback. Okay, so these are the feedbacks given to the NOR gate. If this is R input and this is S input, this would be Q and this would be Q bar. Okay, so this is R, S, Q, Q bar, and this is our NOR gate latch. The truth table for the NOR gate latch would be just opposite to the NAND gate latch. Why we are saying just opposite? You can see the outputs and you can verify it yourself. Like see, for 0, 0, 0, 1, 1, 0 and 1, 1. Okay, so for 0, 0 input, we are getting a memory state, but in a NAND gate latch, for 0, 0 input, we are getting a invalid state, but in this NOR gate latch, we are getting a memory state. For 0, 1 inputs, we are getting a logic 0, or we can say a reset stage. Okay, for 1, 0, it would be logic 1 or it would be a set state, and for 1, 1, it would be a don't care condition, or we can say that an invalid state. Okay, so we can see that, or we can compare from the NAND gates that for all the input combinations, the outputs are just opposite to the NAND gate latch. Okay, so if we want to understand the working, we have to do the same principle or the same working, that is first keeping S equals to 0 and R equals to 0. If we want to check this condition, keep S equals to 0 and R equals to 0 and assume some past outputs like Q equals to 1, Q bar equals to 0, or Q equals to 0, Q bar equals to 1. So we would see that for S equals to 0 and R equals to 0, we are getting a memory state. For S equals to 0 and R equals to 1, we are getting a reset state or logic 0. For 1 0 inputs, we are getting a set state or logic 1, and for 1 1 inputs, we are getting a don't care or an invalid state. So you can make this circuit diagram and truth table, then we are moving towards our different flip-flops. Okay. Now we are going to discuss clocked SR flip-flop. So the difference between the between the latch and the flip-flop can be that in latch there is no clocked input, but in a flip-flop there would be a clock input that would control the working of an latch or SR latch or SR flip-flop. Okay, so there is no much difference there, and there would be 3 possible cases for clocked SR flip-flop. Okay, now first we are going to discuss our first possible case. We are constructing a clocked SR flip-flop by using a NAND gate latch. Okay, so this is our NAND gate latch. This is our NAND gate latch, and this is like this. This is the feedback present. So to give our clock input, we are taking 2 AND gates like this. We are taking 2 AND gates, and here we are giving our initial input, that is S equals to an S and R with having one input as clock pulse. Okay, so now as the clock pulse is present, so it would control the working of this flip-flop. How? By making the truth table we can able to understand. So as there are 3 inputs, that is clock, S and R, we are writing the outputs for all the possible cases. Suppose the clock input is at 0 level. So whatever would be the value of S and R, the output would be, see what would be the outputs. If suppose the clock is at 0 level, it means the output from both the AND gates would be 0 0, and we know that for the NAND gate latch, if the inputs are 0 0, it means it would be a don't care condition. Okay, so it would be a don't care condition. So we can see that on giving clock pulse as logic 0, we are able to control the working of the flip-flop. Now suppose if we give clock as logic 1, now okay, as the clock is having logic 1, now the outputs of AND gate would be dependent on the S and R. Suppose if S and R is 0 0, it means it would be a don't care condition, because clock is at logic 1, and for S equals to 0 the output would be 0, and for R equals to 0 again the output would be 0. So this is the same condition or the similar case for NAND gate latch. Now if we give clock pulse as again 1 and inputs as 0 1, so it would be a set state. Okay, for logic 1 1 0, it would be a reset stage, and for clock as high and inputs as 1 1, the output would be a memory state. Okay, so this is a clocked SR flip-flop with NAND gate latch, and the clock pulse is giving through the AND gates. Okay, now the second possibility is constructing the same clocked SR flip-flop using a NOR latch. So we have taken a NOR gated latch like this, and now we are doing the same thing, that is we are giving the clock pulse through AND gate. So the functioning of the truth table would be same, exactly same as in the NOR gate latch, but when the clock pulse would be at logic 0, thus output would remain in the memory state. Okay, now we are writing its truth table also. So suppose if the clock is at logic 0 or active low input, the output would be 0 0. Therefore, if anything is present at inputs S and R, the output would always remain in memory. Okay. Now if the clock is at logic 1 and suppose S and R inputs are 0 0, then also the output would remain in memory. And for logic 1 as clock and 0 1, it would be in reset state, just opposite to this table. If clock is 1 and inputs are 1 0, it would be in set state. And if at logic 1 and the inputs are 1 1, it would be in invalid state, or we can say a don't care state. Okay, so this was two cases. Now we are discussing the third case, and in this case also we are making it using a NAND gate latch. So for every SR flip-flop, we want a single table to be learned. Like if we want either this table and this table, but this table is more convenient because for 0 0 state we are getting a memory, and when S equals to 0, the output is equals to 0. When S equals to 1, the output is equals to 1, or we can say that set state. And for 1 1, we are having an invalid state. So to make this truth table using the NAND gate latch, what we are going to do, we are going to pass our clock pulse through the NAND gates instead of AND gates. So if we are passing a clock pulse using the NAND gates, this is our clock pulse, and this would be our inputs S, and this would be our input R. Now if we are taking Q and Q bar as output, we are having this same table. So you can mark a equality sign. This is equal sign. We can write also we are having the same. We are having same truth table like in this case, like in B case. Okay, so for SR flip-flop we have to learn this table only, so it would be valid for this clocked SR flip-flop and for this clocked SR flip-flop. This clock SR flip-flop is constructed from NOR gates using AND gates for passing the clock pulse. But for this case we have constructed using NAND gate latch, but we have passed the clock pulse using the NAND gates and using the NAND gates. So for this the truth table would be same. Okay, so quickly write these three cases one by one, then we are going to see our JK flip-flop, and in JK flip-flop how we are able to avoid this invalid state that we are getting. Okay. So let us discuss JK flip-flop. JK flip-flop is known as universal flip-flop because using the JK flip-flop we can construct every flip-flop, that is SR flip-flop also, and we can construct the next two flip-flops, that is D and T flip-flop. So what is the change in the circuit that we have done in our JK flip-flop to avoid the invalid state in SR flip-flop? See, suppose we are making SR flip-flop like this. Okay, this would be a SR flip-flop. So you can able to understand that using a flip-flop we are able to store a one bit of information, and it is also having two stable states. So this is our basic sequential circuit. So suppose this is like clock. So what manipulation we are going to do is that we are giving the feedback from these 2 points to this point. So I mark the connections using which we are able to, we are connecting Q bar to this, we are connecting Q bar and giving it to the this NAND gate like this, and we are connecting Q to this point. Okay, so this is the change that we have done in a SR flip-flop to get a proper state and to avoid the invalid state. So this output is Q and this output is Q bar. So for S equals to 1 and R equals to 1, what is the change that we are getting in a truth table? Now we are going to see that. So suppose we are taking J and K as our inputs and we are giving output, or we are taking output as Q plus. So for 0 0 there would be same state as memory state, so there is no change from SR flip-flop. For 0 1 it would be 0, or we can say reset. For 1 0 it would be logic 1, and for 1 1, okay, for input 1 1 we are getting a toggle state. What we mean by toggle, that is it would be Q bar, that is the next output would be the complement of the previous output. So we are getting here toggle state. So suppose if we are having Q as 0, so the next output, if the inputs are giving J and K equals to 1, would be 1. And suppose if we are having our previous output as 1, so for inputs J equals to 1 and K equals to 1, the next output would be equals to 0. So if we want to write the working also, you can write the working. You can take, assume all the states, and you can also assume the inputs, and using that you can understand the change that we have done in this circuit. Okay, so these inputs were J and K. One more circuit for same JK flip-flop can be also constructed using a NOR gate latch. So if we are taking a NOR gate latch like this, okay, we are taking SR flip-flop with NOR gate, and we are using the same circuit that we have studied earlier. So this is our feedback like this. This is our clock pulse. This is our clock pulse. This is J. This is K and Q and Q bar. What we are going to do, we are just connecting Q with J and Q bar with K like this. So this is the same circuit. This circuit is constructed from NAND gate latch, and this circuit is constructed from NOR gate latch. So the working or the truth table for both the circuits would be same. Okay, so for j equals to j and k equals to 0 0, it would give us a memory state, or we can say that q plus would be equals to q or the previous output. For 0 1, it would give a reset state. For 1 0, it would give a logic 1. For 1 1, it would give a toggle state. So if we want to represent a JK flip-flop, we can also represent it using a block diagram. Okay, so this inputs would be J and K, and the output would be Q and Q bar. Okay, so if we want to represent the clock pulse, this sign represents the edge triggering. Okay, so if we are giving edge triggering to this flip-flop, we use this triangle sign. Okay, so this is the representation or the block diagrammatic representation of a JK flip-flop. So you can make these two circuits and this truth table. Next we are going to see D and T flip-flop. So first we are going to see D flip-flop. So how we are going to construct a D flip-flop? We have to just do some more connections in our conventional SR flip-flop. So suppose this is an SR flip-flop. I am not drawing the whole circuit like this. This is input S and this is input R. We are taking output as Q and Q bar. Okay. So if we make a connection, if S is given as this and R is giving the complement of this, we are marking as D input. So D input is directly connected to S and its complement is connected to R. So what would be the possibilities or what would be the truth table for this case? For D input as 0, S equals to 0 and R is equals to 1. So it means that Q plus would be 0. For D equals to 1, the S input is given as 1 and the R input is given as 0. So it would be a set state, or we can say that Q plus would be 1. So we can say that D flip-flop means that D flip-flop stands for data flip-flop. So whatever data we are giving at the input side, we are getting the same data. That is, for D equals to 0, Q plus is equals to 0, and for D equals to 1, Q plus is also equals to 1. So the whole circuit we can just represent it like this. This is our D input and we are getting Q and Q bar as output. Okay, so this is our D flip-flop. Second is T flip-flop. So how we are going to construct a T flip-flop? T flip-flop stands for toggle flip-flop. So in this we are having two conditions, that is memory state and the toggle state. So to get a toggle state, we have to use JK flip-flop like this. And what we are going to do, we are just connecting it as this, and this is our input T. So what are the possible combinations and what would be its output? For the possible combinations, suppose T equals to 0. So for T equals to 0, J and K would be equals to 0, that it represents a memory state. So it would be in a memory state, that is, the next output would be equals to the past output. Suppose in the second combination, T is equals to 1. So for T equals to 1, J and K would also be equals to 1. And for J equals to 1 and K equals to 1, the state is the toggle state. It means the next output would be the complement of the previous output, that is the toggle state. It would toggle from 0 1 1 0 0 1 1 0. So these are two flip-flops that are the further construction of SR flip-flop and T flip-flops, and there are different uses of these kind of flip-flops in registers and counters. When we study these registers and counters, we are going to see their uses, the uses of D flip-flop and T flip-flop. here you can write the circuit diagram as well as its truth table. Okay, so the block diagrammatic representation we can make also for T flip-flop. This is input T and the output would be Q and Q bar. Okay, so write these points. Then we are going to discuss race around condition that is present in a JK flip-flop. Okay. So I hope you have wrote down these two flip-flops, that is D flip-flop and T flip-flop. Now we are going to understand what is a race around condition. So using a JK flip-flop, we are able to avoid the invalid state that we are getting in our SR flip-flop. But in JK flip-flop, the condition for J and K equals to 1 is not very perfect. What is the imperfect nature of this condition is that is race around condition. So to understand this logic, what we are going to do, first we are going to draw a clock pulse. Okay, this is our clock pulse and this is our pulse width. This is T, P, W. So this is our clock pulse C, P. Okay, and we are taking output as here. Suppose initially the Q is 0. So if the JK flip-flop is level triggered, then the working of the flip-flop will be affected at this level, that is logic 1 level. Okay, so if initially the output is 0, it would change to logic 1. And suppose if the propagation delay of a flip-flop is represented as TPD, so it would change after TPD time. As the level is already present and still present at logic 1, it would again change to logic 0, and it would again change to logic 1, and it would again change to logic 0 up till the logic is at logic 1, that is clock pulse is at logic 1. So here we are getting any output, that is the output of the JK flip-flop is uncertain in this particular time pulse width, because we are not able to understand what would be our final output, because as long as this pulse width is present or this amount of pulse width is present, the flip-flop would be in active mode. It means the output would toggle from 0 1 1 0 0 1 and it would oscillate back and forth from 1 0 0 1, and the output or the final output will remain uncertain. So this condition or this race between 0 1 1 0 is known as race around condition. So the race around condition or the output of the JK flip-flop will depend on the propagation delay of the flip-flop. Okay, and this condition would come when the propagation delay would be less than our pulse width. So what are the conditions for which the race around condition will occur? So the first condition is J and K is equals to 1. This condition is the initial condition or the basic condition, because for the rest of the input combinations there would be no race around condition. The output would remain in stable state. But when J and K is become equals to 1, it would come in a toggle state. It means that when one output, suppose initially here in this diagram we can see that initially the output is at logic 0. So when the clock pulse is level triggered at logic 1, it would change into logic 1, or it would toggle from 0 to 1. But as now the feedback is given to these flip-flops, this one would travel back to at the input, and it would change again the output from logic 1 to logic 0. So it means that it would oscillate back and forth between 0 and 1. That's why it is known as race around condition, and this will happen when j and k is equals to 1. The second condition for race around condition to happen is when propagation delay of flip-flop is less than the pulse width of the clock pulse. So this condition is proved here, as we can see that the propagation delay of the flip-flop is less than the pulse width of the clock pulse, in which the flip-flop is in active mode or in which the flip-flop is triggered. So if this propagation delay is less than pulse width, it would change many times in a given pulse width, due to which the output will remain uncertain. So the main condition due to which race around condition is happening is due to because the propagation delay of the flip-flop is less than our time pulse width. And the third condition due to which this condition is occurring is because flip-flop is in level triggered mode. Because if it is in edge triggered mode, this condition would not occur, because it would be edge triggered only at one time, and at that time the output would be affected of the flip-flop. But due to the JK flip-flop is level triggered, what we are going to see a race around condition or a toggling nature of output. Therefore, the three conditions that are important for the occurrence of race around condition is j is equals to 1, k is equals to 1, propagation delay of a flip-flop is less than the pulse width, and the flip-flop is level triggered. So what is the need to rectify this race around condition? So you can write these points. What is race around condition? For the period of TPW, that is pulse width, the output will oscillate back and forth between 0 and 1, and at the end of the clock pulse the value of Q is remain uncertain. This is known as a race around condition. You can make these two timing diagrams of clock pulse and the output, and you can mark these three conditions for the occurrence of a race around nature. That is j equals to 1, k equals to 1, propagation delay of flip-flop is less than the time pulse width, and the flip-flop is level triggered. Okay, so this is the conditions. These are some of the direct questions that may arise in a GATE exam. So it is very important to understand the race around condition and what are the methods to rectify this race around condition. Okay. I hope you have made all these diagrams. Now we are going to see how we are going to rectify this race around condition. So the methods to avoid this race around condition are: the first is edge triggering, the second is the pulse width should be less than the propagation delay, and this propagation delay should be less than the total time period, and the third is master slave flip-flop. So in this session I am explaining only the first method of edge triggering, and in the next session we are going to see the rest of these two cases. So why we are able to rectify or to avoid a race around condition in edge triggering? So to understand this, first we are going to see the clock pulse in level triggering and what is the difference in edge triggering. So this is the clock pulse for the flip-flop. Okay, to compare we are making one more clock pulse like this. We are making one more clock pulse. Okay, so in level triggering what we are going to do, we are triggering the flip-flop at these levels. So as the level or the activation is present for a good amount of time, there is a possibility to have a race around condition. But in edge triggering, if we are doing a positive edge triggering, that is where we are affecting the inputs or we are affecting the outputs, or we are giving the inputs at the edge triggered, that is when the transition is taking from 0 to 1, like here 0 to 1, like here 0 to 1, then it would we can see that there would be only one change that would be occur at this point, and there would be no change that would occur in this rest of the clock pulse. So if whatever change is done, suppose this is Q, so whatever change is done at this point, suppose this is Q equals to 0, this would change to Q equals to 1 for the J and K equals to 1 condition. Now it would remain up to 1 for the rest of the clock pulse, and this would again change from 1 to 0 for the next positive edge triggering. So we can see that we are able to rectify the problem of race around condition that we are facing in level triggering by using the edge triggering. So this is the benefit or the advantage of edge triggering in JK flip-flop. Okay. So the rest of the two conditions we are going to see in the next session, and in next session also we are going to see the characteristics table, excitation tables, and how we are constructing different flip-flops using JK flip-flops. Okay, thank you.